Sure.
Okay, so welcome to the second plenary talk of the Brazilian Colloquium of Mathematics. It's for me a great pleasure, an honor for me to introduce our next keynote speaker, Professor Georg Weiss. Professor Georg Weiss got his PhD from Bonn in Germany under Professor Willy Alt. And after that, he got a very distinguished fellowship, Humboldt Fellowship, and then he went to Japan. And there he became a professor, assistant professor, and then associate professor at Tokyo University. In 2010, he returned, he moved back to Germany, and now he has a very distinguished full professorship position in Duisburg-Essen. I'm sorry for my German pronunciation. And he is very well known in the theory of free boundary problems. He is best known by a series of striking results on monotonicity formula. And he's gonna give a talk today on singularities in ElectroHydroDynamic equations. So thank you, George.
Thank you very much. So this is a great honor giving a talk at this colloquium. And so coming back from very macroscopic things, I would like to have a look at an experiment done in the 60s by Sir Geoffrey Taylor on a more microscopic phenomena. So let's consider a liquid coming out of a nozzle. And so in the nozzle, you put a pressure on that liquid. The liquid should also be a perfect conductor, okay? And outside, so in the real experiment, you have some metallic cylindric object outside the nozzle where you also put some voltage. So you have a voltage difference between the liquid and the outer, well, the cylindric containment, which we will later consider to be infinity, and that drives the experiment. And what Taylor observed in the experiment is that when you increase the voltage, then first you get some curvature on the surface of the liquid. And the interesting thing is when you increase it further, then it approaches a conical shape. So the conical shape, you don't put any freak data on the outside that produces a cone, but that the cone appears by the equations. Actually, that's the interesting thing. And then at the critical voltage, you obtain almost a mathematical cone. So that's very interesting. And of course, that cone should be unstable, which it is, so it ruptures then. And then afterwards, a tiny fluid jet separating into droplets appears at the tip. So mathematically, we would say you obtain a cusp at the singularity, a cusp singularity. And the thing is that from the point of view of mathematics, there are almost no results on this phenomenon. Well, there are a lot of applied mathematicians' results, but those are using very complicated models, and a large part of those are numerical results. Actually, this phenomenon has a lot of applications because it produces a very focused spray of liquid. So you can imagine that that has applications, even going as far as inkjet printers, mass spectrometers, and the production of lab-on-the-chips. And there are two stages in the experiment, or actually two phenomena that you could have a look at from the point of view of analysis. And one of them is the stationary fluid before rupture of the surface, right? So first you obtain this curved surface, and afterwards you obtain this probably unstable, although that has never been mathematically proven, the cone. And afterwards, you obtain this jet, and that is also, a stationary fluid jet. So that's another regime you could study analytically. So, but both are almost, there are almost no mathematical results on either of those. The only result is that is known is existence of the cone, which is then called the Taylor cone, and that is a result by Geoffrey Taylor himself. It's very simple. You just do spherical harmonics, and then you recover the Legendre function of degree 1/2 produces the Taylor cone, which is with the standard parameters, it's a cone of roughly 98 degrees. So this is not a magical number. This is related to the zeros of the Legendre polynomials. Okay. And but we are using the simplest models available for some mathematical analysis. So we are applying the Euler equations for an incompressible inviscid and perfectly conducting liquid. And outside, we suppose that we have a dielectric gas. So also we ignore this containment, which is in the actual experiment by Taylor, it was a cylinder. And we suppose that everything is driven by the difference of the voltage at the liquid and infinity. And also the influence of gravity is tiny on that cone, so we also neglect that. And then we obtain the EHD equations. So you obtain a harmonic function. So if phi is the velocity potential, V is the velocity potential, then V is a harmonic function in the liquid. And so phi is the electric potential, and that's also harmonic in the gas. And then you obtain a Bernoulli type free boundary condition on the surface. So the gradient phi squared minus gradient V squared should equal the curvature plus some constant on the surface of the fluid. And you obtain now the not so standard thing is that you obtain Dirichlet and Neumann condition for the two phases on the free surface. So the phi should be constant. Well, let's let it be 0 on the free surface, and also V should have zero Neumann condition, satisfy zero Neumann condition on the free surface of the fluid. So B is a constant, then V is as I said, the velocity potential of the fluid, and nu is the outward unit normal on the surface, and kappa is the mean curvature on the free surface, and the sign of that mean curvature is now going to be very important, because when you change the sign, you get a totally different model. So, and the sign is chosen so that the mean curvature is positive for convex phases, okay? But it will become more clear in the variational setting I'm going to show you in a few seconds. And as a free boundary, looked at it as a free boundary problem, this is new. So analytically, the problem has not been really studied. And particular difficulties are created by the Dirichlet to Neumann conditions on the free surface. So, Neumann free boundary problems are notoriously difficult. So those have only been successfully treated in 2 dimensions where you can switch to the stream function. Actually, we are doing something similar here too, or in the axially symmetric 3-dimensional setting where you can use the Stokes stream function. Yes. But in 3 dimensions, Neumann problems are even by some authors looked at as ill-posed. So they're not really, even close to flat surface, there are not any good results in the real 3-dimensional problem. If you change the sign of the curvature, then there are actually some mathematical results. So there's there's a series of papers starting with a paper by Athanasopoulos, Luis Caffarelli, and Sandro Salza in 01. So here, the important thing that the sign of the curvature has changed to minus kappa. Okay? And then the problem becomes a well-posed one for reasons I will point out in a few seconds. So let's write down the energy of the problem. So if you look at one-phase solutions, so let's say the U minus is 0, that means in our problem we ignore for just a few seconds the fluid flow, okay? Then the energy is the perimeter of the phase where U is positive plus the Dirichlet energy, or that would correspond to some kinetic energy if you want, right? And so this is in the setting of this work by Athanasopoulos, Caffarelli, and Salza. So here you see you have a sum of two positive energy parts, right? Whereas if we look at our problem, so with if you neglect fluid flow, so V is 0, and let's take B equals 0, then our energy is minus perimeter plus the kinetic energy, right? So you even if you look only at the existence of the problem, so you cannot do any minimizers make no sense here because you have one energy minus another positive energy. So you would have to look at saddle points. And that creates also huge differences in the analysis. But so in this problem, in the stable problem studied by Athanasopoulos, Caffarelli, and Salza, there's actually a nice result. So you can show regularity up to dimension 7. So that's a result by Zhang, Larsen, and Silvestre in 2011. In our problem, the one-phase problem actually turns out to be in a certain, with certain assumptions to be equivalent to the Mumford-Shah problem. So let me say something about the Mumford-Shah problem because not everybody is familiar with that. So that was some model introduced by David Mumford and Shah with image segmentation in mind. So you have some gray scale data and you want to detect edges in that image, right? And so the edge in the model is a discontinuity set, and you don't want to introduce too many edges. So this is the penalty for introducing too many edges. So the penalty is the Hausdorff measure of the edges. On the other hand, the variation of your of the smooth part should not be too big. And the problem is that, apart from some flatness imply regularities results, which are valid only for minimizers, in this problem, there's not much known. So it's not much is known about singularities. Well, there's the famous Mumford-Shah conjecture in 2 dimensions. So in 2 dimensions, the conjecture is that there should be only triple junctions and crack tips. But that's open, even in 2 dimensions. And the singularities in 3 dimensions, which have something to do with the Taylor cone, actually, are completely open. And that's even for minimizers. So even those flatness imply regularities results I mentioned are only valid for minimizers. They are not critical points of this function have not really been studied at all. For that, you would need a varifold theory and so on and so on. It's not easy. Okay, so here's the first variation of that Mumford-Shah functional I wrote on the board. So you obtain outside the discontinuity set, you obtain a harmonic function, and then the jump of the gradient squared equals curvature on the free discontinuity set, where now the sign of the curvature is the bad sign, as in our problem, so as in the EHD equations. And you can apply that actually it has something to do both with the electric phase and the fluid phase. So if you neglect the electric phase, then you recover immediately in the Mumford-Sharp problem, but a one-phase version of that. And even in the electric phase, in 2 dimensions, you could switch to the stream function, so you can take the harmonic conjugate and again recover the Mumford-Sharp problem, but that works only in 2 dimensions. In 3 dimensions, you could still use Stokes stream function, switch, and then but then you recover, it's not a harmonic function, but you recover another, your equation changes. That also means that with certain assumptions, you can apply results for the Mumford-Sharp problem to our problem. And so that means you can also apply some results done by my group in 2 dimensions. So now let me make 2 remarks on scaling in that problem. So when you at first look, you could look at homogeneous solutions of the problem, which actually Taylor did. So assume that the free surface is a homogeneous surface. That means that the mean curvature scales like 1 over r. Okay? And that means that also gradient phi squared has to scale like 1 over r, and gradient v squared has to scale like 1 over r. That means that both should be functions, homogeneous functions of order 1/2, right? So and that the constant in this case, the constant b should be 0. And that you can write down with Legendre functions, and you recover the Legendre function found by Taylor, which is p1/2, and that the 0 of that Legendre function gives you the angle of the Taylor cone, which is 98.6 degrees. So this picture, by the way, is taken from the book by Eggers and Fontelos, who actually pointed out that problem to us. So the second remark I have on scaling is, so let's consider small cylinders. So now I'm thinking of the cusp, right? So in the experiment, we saw a cusp forming. So now I'm ignoring completely the separation into droplets. That does not really interest us. But close to the cusp tip, this free surface looks like a cylinder. So therefore, it's just to get some impression of scaling, it's not unreasonable to look at the situation of a cylinder. So let's look at this situation. So you take electric potential 1 on a large cylinder, and then you take the electric potential equals to 0 outside, and in the middle it's harmonic. So what you obtain is, of course, the capacity potential, and that you calculate, and you get that phi equals some constant and then the logarithm of S over R. And then that you plug in that into your free boundary condition, and then you obtain this equation. So curvature plus constant, so that's 1 over r plus constant, equals the difference of the 2 gradient squareds. And 1 you can compute, so that's 1 over r squared log 1 over r squared. So and this suggests that close to the cusp, the surface tension is negligible to the other part, at least with respect to this part. Also, the constant is, of course, negligible. And that means that close to the cusp, if you are interested in the formation of the cusp, you are allowed to neglect the curvature and also the constant. And that's what we do in this talk. So it looks now really, really almost trivial. So you have 2 harmonic functions, but you still have the coupled, the Dirichlet to Neumann coupling, which makes it actually a new problem. So we also ignore the separation into a spray of droplets. We neglect the surface tension, and then we come up with the following problem. So we have two harmonic functions in the gas and in the fluid, and we have this, well, I would not call it really Bernoulli type free boundary condition anymore. Anyway, the length of the gradients has to match on the free surface, and we still have the coupling of Dirichlet and Neumann condition on the free surface. So it looks fairly simple. And to make it even simpler, we confine ourselves to an axisymmetric setting. So in that case, we can use the Stokes stream function. And that means we have a change equation in 2 dimensions. So we use, well, if you want to write down the original velocity field, then the velocity field capital V of x, y, z would equal to minus 1 over 1 coordinate, let's call it x1, and second derivative of u minus cosinus theta, and so on. So the original coordinates are given by x1 cosine of the angle, x1 sine of the angle, x2. And then you obtain, two equations with variable coefficients in the 2 phases, coupled still by this sort of Bernoulli type free boundary condition on the free surface. And now you may think, because the only thing that jumps on that free surface is the coefficient, right? The coefficients jump from x1 to 1 over x1. Now you could think then that you can apply some standard transform, like, for example, the so-called Kirchhoff transform, and transform the problem into a regular problem. And that does not work because, so it would work if this free boundary condition was compatible with the 2 equations, but it's not. So in other words, this does not really have the necessary variational form you would need for that transformation to work. So you cannot take the easy way out. Okay, now let me tell you a little bit about how we arrived at that problem. So we came from water waves. Where you have a free surface in between, let's say, air and, let's say, water. That means here you consider the 2D Euler equations incompressible. And inviscid in this case. And so here you get 2 free boundary conditions. One kinetic free boundary condition that tells you that if the free surface moves, then the molecules in your liquid also have to move. So this is very natural. And the other condition is that is a condition, the so-called Bernoulli free boundary condition, which you recover from the Euler equations themselves. So, and when you consider a stream function psi, then you obtain Laplacian psi is 0. So in the irrotational case, and psi is 0, let's say, and gradient psi. So here I don't neglect the gravity, so that should be y on the free surface. And then, actually, Stokes considered that problem. And actually, Stokes looked at waves on the river Thames, and then he observed that, well, sometimes it looks at that, but then the amplitude changes, and sometimes he got waves with a sharp crest. And then actually Stokes conjectured that the angle of that crest should be 120 degrees. And at that time, that was there was dispute about this because Rankine conjectured at the same time that the angle should be 90 degrees. So it was not clear. And when you look at actual waves, you see that you cannot easily settle that dispute by experiments. Well, now actually English mathematicians are doing experiments in some small channels, but I think in the 19th century that was not as easy. Anyway, Stokes actually proved formally by using an asymptotic expansion, using harmonic polynomials, this conjecture of 120 degrees. And so we proved that it was later proved by Amy Toland using Riemann mapping theorem and so on, but in a hugely sophisticated paper. And we proved that by different methods. So actually working in the original coordinates, it's very interesting. So for a very long period, most papers on the water wave problem have not worked in the original coordinates, but always used the Riemann mapping theorem. And so that has the advantage, of course, that you transform your surface into a flat surface. So the boundary is then a fixed boundary. It looks very nice. But it does not necessarily make the mathematical analysis easy. And the papers are quite sophisticated. So, and our results relied on introducing a Lyapunov functional in the original variables. And that way we could prove the Stokes conjecture. And even in the case of vorticity with certain assumptions. But the interesting thing is that we also used a so-called frequency formula. Well, for that I should mention that if you have a harmonic function, then this mean frequency found by Alencar, so this is the famous frequency formula by Alencar, then this quotient is non-decreasing in R. Okay? And we found that at the singularities here, if you take the difference of the two energies, so here also you have the energy corresponding to these equations is gradient psi squared plus y characteristic function of so this would be the water phase. And then if I reflect at the y equals 0 axis, then I get this energy in the problem. But to extend Alencar's frequency formula, we have to take actually the difference of the two energy parts. So this is minus y then. And it does not work at any point like Alencar's frequency formula, but it works only at points of highest density. So that it's actually kind of amazing because, well, Alencar's frequency formula worked for harmonic functions, but if you change the equation to some semi-linear function, which this is kind of, right, if you take Laplacian v equals g of v, then there's no frequency formula for any of these equations. But our result there would actually tell you that at certain points, at point of highest density, a frequency works there. Okay, so we came, and that works even if you have a reaction term, right? This is a reaction term, and even then you can somehow study singularities that way. So now looking at our problem, we thought, so here there's no reaction term, right? So you have two harmonic functions coupled by some boundary condition. So we thought it would be that easy, and you would certainly get a frequency formula there. Let me also give you some more background. So so by the way, this our result on waterways was that was done with Eugen Barbaruka, and we even extended that to the axisymmetric setting in. So there we used again Stokes stream function. So that is now very much related to the equations I showed you before. So here we get the same equation for the Stokes stream function. So the divergence of 1 over x1. So it's singular on the axis, but it's not a big problem. Gradient psi is 0 in the water phase, and then we get this Bernoulli condition. Now, if I put the x1 squared on the right-hand side, then that would be minus x2 x1 squared. And again, the original velocity field would be given by the Stokes stream function like this. And the original coordinates x, y, z are given by this formula. And then, so in the waterway setting, you've only two cases and two different scalings. So away from this y equals 0 axis, you are on the regular regime. And so when you look at the free boundary point with a microscope, then it's always straight. Okay, and on the axis y equals 0, our result shows that you always get the Stokes corner, you always get an angle of 120 degrees. By the way, this result is, when you look at the time-dependent problem, then it's completely open. So you could look now at pulsating waves depending on time, and then well, those should form singularities for countably many times, right? And then you could ask, what is the angle of the pulsating wave at the singularity? And now, amazingly, it's again the same conjecture, or the same two conjectures. There are again people who say it forms an angle of 90 degrees, so going back to Rankine, and people who say it should be 120 degrees. There are even people who say it's completely unstable, it oscillates, and you don't get any sort of self-similar profile at the singularities of the time-dependent of the space-time periodic solution. But okay, so that's just for background. Anyway, in this problem, we had two different regimes, but now we have this axisymmetric setting. So this is the x1 coordinate, and this is the x2 coordinate. And now there are more regimes, so, right? So this x2 equals 0 corresponds to y equals 0, right? So here you expect sort of the Stokes corners again. And, but you also have the axis where something might happen. At least the equations become degenerate or singular on the axis. So something could happen there. So you can have the regular points should still be regular. So, and then here, away from the axis x1 equals 0, but on the axis x2 equals 0, you would expect the Stokes corners. But if you have gravity, But on the axis, something new could happen, and that was the topic in a paper with Eugen, which has appeared in CPAM. And there we have, of course, 4 invariant scalings, or 4 scalings to look at. So one scaling is, so if you use the Stokes stream function, the scaled function psi over r at the regular points. So that's inside this quadrant. And then we have the Stokes corner scaling, that is the stream function divided by r over the 3 over 2. Here, for x1 equals 0. And on the axis, it turns out that the scaling to look at is psi, the scales by as psi over r squared. And then a new point is now the origin, because here both are degenerate. x2 is degenerate and x1 is degenerate. So the invariant scaling there is has exponent 5 over 2. But that's the scaling of the stream function. So if you go back to the velocity field, then the scalings would be 1. So constant velocity x squared. So distance to the to y equals 0 squared, 1, and again x squared, root x. And so in the regular case, of course, you should recover only constant velocity flow as asymptotics, and that's what we got. And on here we show that the only thing you get is Stokes corner points. So the situation at points like this was interesting because it was new. And here we show you recover only constant velocity flow. But that gives rise to the possibility of cusps, right? So you could have cusps one way or the other. So tiny air cusps close to the axis. That is allowed by the model. And the last case, interestingly, has only one possible asymptotics, and that is the so-called, that has already been found by Garabedian, and that's the so-called Garabedian bubble solution. So what Garabedian imagined was some air bubble rising in liquid. Okay, so here you have the liquid, and here you get some wide angle. And then, well, if you fix this point, then actually the fluid flows down, right? But that is not compatible with our model, right? So we are looking at water below air, or we were looking at water below air. So, so there were no possible solutions at all. So if you you would have imagined something like this, considering a fountain or something like that, right? If you look at the gusher or anything like that, it does not even matter whether you look at it in a moving frame or velocity 0, because you can look at the equation in the moving frame, and then the origin is always 0. So a solution like this should physically exist, but we could not recover it in this analysis. So that was very strange. So the only, because, well, solutions like this would be allowed where you have a cusp on the axis. So this is allowed, but something like this was not allowed by this first order analysis. So that was surprising. But then we did a finer analysis, and that involved degenerate points, so points where the invariant scaling is not right. So So we had 4 invariant scalings, right? And to see what happens if these invariant scalings lead to a non-trivial limit is rather easy. But when none of them is right, so when the invariant scalings are not the right scalings, then it becomes really hard to do. And that's where we used this type of stream function and recovered that there the velocity field behaves like a constant times square root of x squared plus y squared to z. So we actually get something like this with a linear, the velocity has a linear asymptotic profile at that point. So it's not, and the key in the analysis was a frequency formula. And so we expected, because the EHD problem does not even have a reaction term, so we expected it to be much easier. So this is the EHD equations with curvature neglected. So it looks really, really easy. So we even can transform. We transformed this Neumann condition into a Dirichlet condition using the Stokes stream function. So now we expected that some frequency function should easily work. But it did not. So we worked on that for about a year with Mariana, who is here, and Eugen Wawaruka, and we could get no result on a stream function. So nevertheless, we got a result, which I would like to show you now. And so for this EHD problem, if the free surface is given by a continuous injective curve, and if for some given gamma, one of the, well, you have 2 phases now, U plus and U minus, corresponding to the electric field part and the fluid part. Okay, and so if there are, one of them is non-vanishing in the limit, so bounded from below like that, then the result says that you converge to cusp. So the free surface is asymptotically cusp-shaped. So that's, of course, a result away from the Taylor-Cone problem. So that means that the Taylor-Cone, for the Taylor-Cone, the gamma has to be bigger. And so we don't get any result on the Taylor-Cone, which was as expected, because for the Taylor-Cone you need something, you need a different analysis. But here we focus on the cusp regime, and we can show that asymptotically it's cusp-shaped. So in the mathematical or analytical keys to this results were 2 Montanisti formulas, so 2 local Lyapunov functionals. One of them is of Al-Kaffarelli-Friedman type. So there's this famous result by Al-Kaffarelli and Friedman. And so when you have 2 harmonic functions, let's call them V and W. And let's say they are both 0 here. Then the product of the scaled Dirichlet energies, let's call this omega 1 and omega 2, is a non-decreasing function of R. And the critical case in this ACF formula is the case where both are half spaces, okay? But here we show an ACF type formula for our equation with weights. And then, so this is the energy, so that's not surprising. But now you get, of course, a different angle. So the critical case is not. So this formula is symmetric with respect to both phases. So it's natural that the critical case should be a half space, right? So this converges when R goes to 0, either to the case where one phase vanishes completely or to the case where both match. And that is the half space case. And that is, well, the formula is actually proved by considering an eigenvalue problem. And the critical case is when both eigenvalues match in their case, but not in ours, because now we look at the weighted problem. And but still we can show this formula with a beta star, which we determined only numerically because we can solve the corresponding eigenvalue problem only numerically. So in the ACF case, it was easy because, I mean, the half-plane case, so there the angle is completely clear. But in the other cases, unless you're really, really lucky, the angle is going to be some crazy number. You get either numerically or it's related to Legendre functions, but it's not a number, it's not necessarily a number that makes a lot of sense. And that is the beta star, which was, I think, numerically 7 point something. But this ACF formula alone did not lead to the result I just showed you, so we need another one. And so here you use the energy, the natural energy of the problem. So let's call the energy of U plus I plus and the energy of the kinetic energy of the fluid phase I minus. And we also use the L2 norms on the spheres, J plus and J minus, and put that together. So here it's interesting because you see that now the plus part and the minus part have different scalings. That's not looking at the original problem, that's not understandable, but that comes from the Stokes stream function, right? So introducing the Stokes stream function, so even if you have a fluid, the gradient of the velocity potential of the fluid and the electric, the gradient of the electric potential scale the same way, then now that's not true anymore. So introducing the psi, the Stokes stream function, so we introduce a difference of order 1 between the two phases. And that's reflected in this formula where you have beta and beta plus 1. So still, then this is a localized Lyapunov functional in the sense that the derivative of m is non-negative. And if it's 0, then both phases are homogeneous functions, but homogeneous, of course, of different degree, right? So when this is 0, then the U plus is homogeneous of degree beta, and U minus is homogeneous of degree beta plus 1. So this you could immediately apply to characterize limits in the case where you have a fixed scaling. So if you know that U plus and U minus behave like R to the beta or R to the beta plus 1, as R goes to 0, then you could apply this and obtain results. But in our result, you don't know that, right? So the scaling could oscillate widely as R goes to 0, and still we obtain that the limit, that the surface is cusp-shaped in the limit. And this we obtained by a combination of the two formula, of the ACF formula and this formula for M. And so last, I would also like to mention regularity result away from the axis. So before I told you that you cannot easily transform the problem into regular problem, but away from the axis, that's actually not true. So if you stay away from the axis, then you can use this transform. So you define v as x1 times u plus and u minus. And now this is, turns out to be a regular function. And you can actually apply a classical result by Lois, Caffarelli, and Avner-Friedman and obtain that away from the axis, your free surface is a smooth surface up to finitely many singularities. So the outlook is that the first result I showed you, so this ACF formula, this is still valid even when you have surface tension. So you can apply this even in the case of surface tension. The problem in the case of surface tension is to characterize global solutions, which is not so easy. And we are working on that at present. But there's hope to get a result even in the presence of surface tension. Thank you